introduce Mustafa Amin, who doesn't really need an introduction. Mustafa did his PhD at Stanford. He then became a Pappalardo Fellow at MIT. And after that, went across the Atlantic, across the pond to the University of Cambridge, where he was a Kavli Fellow. Upon returning from Cambridge, he came to Rice as assistant professor. And Mustafa has done very vibrant research in cosmology, of which we'll hear more today. And I'd like to add also that he's a very vibrant teacher, and he very deservedly got a, Mustafa, help me here, the name of the award. It's a teaching award awarded by the Graduate Student Association, is that correct?
Yes.
Yes, and that was last year, prior to all the chaos related to the pandemic. So with this, Mustafa, go ahead, please.
Right, I'm gonna share my screen. Can everybody see the screen? Yes, okay, great. Andre, do I need to do anything about pinning the video or anything, or it should be fine?
No, it's already pinned, I took care of it.
Okay, all right. Thanks everyone. It's a great pleasure, of course, to give this colloquium. I wish it was in person, but such is the situation. This is the way it is. I'll try to do my best to convey the excitement of some of the things I've been working on. And in that vein, the topic I've chosen today is really something that's excited me for a long time, and I've continued working on this, and there are some exciting news results that I want to share with you. And the topic I want to talk about is about solitons in cosmology. But before I tell you what solitons are and what this topic really is, I want to start with a movie. Hopefully you are seeing this. Can you guys, was the movie choppy or was it pretty smooth, Andre?
I'm muted. I think it was all right, but you
let me try, give me 1 second. Let me just, I think I want to do something again to make sure it plays smoothly. Okay. So this movie will play again. So this is the movie I want to start with. And this movie is about the density in some field, okay, that I'll talk about later. And the lighter colors correspond to high density regions, and the darker colors correspond to low density regions. This is a three-dimensional simulation, and this is a projection of those three dimensions onto the screen. As you saw this movie, hopefully you also saw that initially there was an almost homogeneous distribution that very quickly fragmented into these localized lumps. Okay? The title of solitons that I use, these lumps are what are solitons in this movie that you see. Now, the goal for this colloquium for me is very simple. Okay? What I want to do is I want to tell you why what you saw is relevant for cosmology. What is it that's actually going on? And what are the observational implications? So if you walk away knowing these three things, then I'll think that I've delivered the colloquium successfully. Okay. So in the vein of why is this relevant for cosmology, my claim is that this simulation in this movie that you saw is relevant for what happens in the very early universe at the end of inflation. And it could also be relevant for dark matter, in particular a type of dark matter called axions, both in the early universe and in the present day universe. So that's the context in which the simulation that you saw is relevant in understanding. Let me give you a broad overview of what inflation is and what dark matter is. So to put this in context, so here is sort of our big cosmic story. If you ask a cosmologist today, what is the story of our universe, they'll say something similar to what I'm about to say. They'll say that in the very early universe, the universe underwent a very rapid accelerated period of expansion. This period is called inflation. The energy density that drove this period of inflation got transferred to the particles that you and I and everything is made up of. So that's the process called reheating. During this really rapid exponential expansion or accelerated expansion of inflation, quantum fluctuations, which are of course always present, got stretched out to humongous scales, cosmological scales. And the matter that formed afterwards inherited these fluctuations in them. That is, there are density fluctuations in the distribution of matter, which arose from initial quantum fluctuations that are present, that are always present. We can see these density fluctuations really well in the cosmic microwave background. This is this orange and yellow and blue plot that you see. This is basically a picture of the universe from the time that the first atoms were formed. And we can see these tiny fluctuations in density at that time. After that point, essentially gravity takes over with the aid of another component which makes up about 85% of the matter in the universe called dark matter. Gravity takes over and it takes these small density perturbations and makes them clump. Okay? It makes them grow and things clump together under the influence of gravity. Turn the clock 14 billion years forward and eventually you have all the galaxies and stars and everything that we see in the sky today. And ultimately, of course, that leads to us. So that's sort of a cosmic story. And as you can see in this cosmic story, two parts were important. Okay? One is this period of inflation and this idea of dark matter. Both of these are important ingredients, but we don't know all the details about what this stuff is. So the simulation that I showed earlier, it is possible that the dynamics that I described, or at least showed visually, is happening at the end of inflation in the field that drove inflation. And it's potentially also happening in the dark matter, in this particular type of dark matter called axions. So that's the context in which the dynamics I'm going to describe fits into the big picture. Just heuristically giving you a sense of scale for this. If this process is happening in the early universe at the end of inflation, then these scales are microscopic. They can even be subatomic, okay? Much smaller than the atomic size, in fact. But if this phenomena that I'm describing is happening in dark matter, then these scales could be macroscopic, but usually smaller than the scale of the galaxy. And it might seem confusing, why am I talking about the same phenomena in two very different eras? And hopefully I'll try to convince you it's because this phenomena that I'm talking about is quite general. And it will apply to somewhat general situations which are satisfied by both this type of dark matter and by the inflaton field at the end of inflation. All right, so hopefully I have given you a bit of motivation for why the dynamics that I showed in the movie is relevant. Next, I'm going to turn to describing what these dynamics are in detail. I'll give you slightly more technical aspects of it, but then revert back to talking about things visually. By the way, as it has been with previous colloquiums, please feel free to ask me questions during the middle, and Andre will hopefully tell me if there are questions in the middle. Please interrupt me along the way. I'd much rather you interrupt me in the middle and just wait all the way till the end.
Yeah, I'd suggest, because there are about 60 of us, if people could raise their hands, I will see them and give the mic to them, please.
Okay. Thanks, Andre. Okay, so now let me tell you a little bit more. I've already used the word soliton in the title, and I used it before without telling you what a soliton is. The first thing I want to do is tell you what a soliton is. So in simple words, a soliton is a very long-lived, in principle, infinitely long-lived, but usually for physics purposes, just very long-lived dynamical excitation of a field, right? In which usually an excitation of the field tries to disperse, okay? There are dispersive effects that try to disperse the excitation away. But here, nonlinearities prevent this dispersion. So it's a long-lived dynamical excitation of the field where the nonlinearities balance out the dispersion. So solitons have a very long history. Okay? Indeed, in 1834, there's this story about John Scott Russell. He was sort of riding on his horse along a canal near Edinburgh. And as he was riding along this canal, a boat came to a stop and created a pulse of water in this canal. And he saw that this pulse of water traveled for a few miles. He tried chasing it on his horseback without changing much of its shape or size, and it kept on going, right? So this is an example of this excitation that travels without distortion. Usually, if you think of a ripple on the surface of a pond, it will dissipate away. But this one didn't dissipate and traveled for a long time. So here, in this context, the field that I'm talking about is, of course, the height of the water above the quiescent level. It's a function of space and time in this sense. So that's what I mean by field. Now, this was the original discovery of the solitons, but they've been found in optics and hydrodynamics, in Bose-Einstein condensates, in high energy physics, and also, as I'm going to talk about, they haven't been found, but there is good reason to believe they also exist in a cosmological context. So they have a long history. Now, here I told you that what I mean by a field in this context is just the function, the height of the water as a function of time and position. But what is the field that I'm talking about in the context of the movies that I showed you? For the next 3 slides, allow me to get a little bit technical because I really have to tell you what I'm doing. But after that, I will revert back to showing all my results in the context of visual movies and simulations. So the field that I'm talking about that you saw the movie for is actually a simple real valued scalar field. Its action is shown above. It has both gravitational interactions, meaning it is in the context of general relativity, if you want, and the field, the particles that make up the field also have self-interactions, meaning they can talk to each other. In this field theory language, the particle self-interactions are governed by this potential V of phi that you see here. If V of phi was just m squared phi squared, that it was quadratic, you would say it's a free field. But if there are some nonlinear terms here, then you say that the field has self-interactions. The type of dynamics that I'm describing correspond to this potential V of phi having a shape that opens up away from the minimum. An intuitive way for thinking about this opening up away from the minimum is to think that the particles that make up this field have an attractive self-interaction. Okay? So they try to attract each other beyond what would just be there from gravity. Now you might ask, so there are scales in this problem. There's m squared, which is the curvature of the potential at the bottom, and there's capital M, which is a scale where the potential changes from quadratic to something else. So these scales will play a role, but I'll mention them as they come out. So in condensed matter systems, for example, if you're dealing with BECs, the interactions come from interactions between atoms and things like that. So how do you find the shape of this potential? Okay, where does this shape of this potential come from? And remember, this is the shape of the potential for the field, not some external potential that is provided. So this shape in cosmology sometimes comes from observational constraints, and at other times it comes from theoretical considerations. Okay, both of these things play a role. To give you an example, if this scalar field is an example of a field that drives inflation, then observations of the cosmic microwave background give us some constraints on what the shape of the potential is. So they tell us that this shape is flatter than quadratic away from the minimum, and then the natural thing to do is to give it a quadratic minimum. So that's one way in which you get it. There are also theoretical motivations for why this shape should come about. Similarly, in the context of this type of dark matter that I'm calling axions, which were initially proposed to solve the strong CP problem, another way of saying it is why is the dipole moment, electric dipole moment of the neutron so small. This was proposed in that context and then it was realized that the solution can be described as a field which is very weakly interacting, so it can play the role of dark matter. So there again, there are theoretical considerations that tells you the shape of this potential. And I'm not going to go into the detail here, but please feel free to ask me afterwards if you're interested. So the shape of the potential is given by that. And in both of these contexts, there's a natural tendency for these potentials to have it opening up away from the minimum. One more technical thing that I want to mention is that as far as we know, the fields that we find in nature are quantum fields, gravity aside, which we don't know the full details of yet. Okay? They're quantum fields, but I'm going to treat these fields classically. And I'm going to, instead of treating, and when I say treat fields classically, I'm going to still treat it as a field, like we treat an electromagnetic field classically, not as individual particles, like you would say, treat tennis balls. Okay? To just give you a sense of why I'm able to do this, the reason is that these fields that I'm talking about have very large occupation numbers. So even though I can treat them classically, which means I can essentially think of h bar going to 0, the occupation number of these fields, n, is quite high, which gives finite momentum and energy for the states of this field. So I can, again, there are many subtleties here. I can roughly treat them classically. Okay? If you wanted to treat this as classical particles, you would have to think about really localized packets, which have a very small wave number, still with a finite momentum. So the new thing I'm doing here compared to how usually people treat dark matter is that here I'm treating it as a field rather than just an incoherent correction of particles. But it's still a classical field at the end. Quantum mechanics plays a role, and I will mention it, but not in the time evolution as far as it is. But there are lots of subtleties here, but this is more a slide to make myself feel happy than to make everyone else feel happy, just because I want to make sure I put it out there that there are assumptions underlying. Okay, so that's the end of my technical slides. Now I'm going to go back to describing things in visually. So the first thing I want to do is show you the time evolution of this field. I already showed you a movie in 3D, but now I'll show you the same evolution in 1 dimensions, because I think it's much more obvious what's going on in that case, and then I can describe what's going on as well. So all I'm going to do is solve a nonlinear Klein-Gordon equation for the scalar field. On the vertical axis here is the amplitude of the field. On the horizontal axis is space. The green line indicates the initial conditions for this field, which is roughly homogeneous. This is, for example, the initial conditions that you would find at the end of inflation. Importantly, it is not perfectly homogeneous because quantum mechanics would tell me that there have to be some fluctuations there. So even though you can't see the green line have fluctuations very easily, there are small fluctuations in there. And in this movie that I'm going to show you as it evolves forward, the shape of the potential is shown here, but I'm even ignoring gravitational interactions. Space is expanding, but I'm ignoring gravitational interactions between individual particles here. So let's see what happens in this case. So I let the field go. You see that the field initially starts oscillating as a homogeneous field, which is sort of like a harmonic oscillator. It just moves up and down. But very quickly, the field stops being homogeneous. There's an instability that spatially fragments the field into these localized structures. These localized structures are similar to the solitons that I was just describing a few minutes ago. So this is what's going on. So you notice, first of all, the first thing you might have noticed, and if I can play the movie again, you notice that there was an instability that took a homogeneous configuration and make it spatially inhomogeneous. So what is this instability? What is going on? So the instability, really what's going on is the phenomena of parametric resonance, okay? Or more technically, it's a Floquet instability. What's going on is that the homogeneous mode that's oscillating acts as a time-dependent periodic frequency for the fluctuations. And this time-dependent periodic frequency ends up making the fluctuations grow exponentially fast. So that's the instability that's taking place here. This is a Floquet diagram. It tells you for a given amplitude of the field, which wave numbers are excited. The light colors mean those wave numbers are excited, and there are these Floquet bands that come about. This is somewhat technical, but if you want to know an example of parametric resonance, which is same mathematics is at play, many of us are familiar with this, which is that of a person on a swing. So here my friend Paula Rebusco is demonstrating this. So if you're on a swing and you change the length of the pendulum periodically by standing up and down, you can make the arc of the swing grow really, really rapidly. Nobody's pushing you from outside, but you are just changing the length of the pendulum periodically. The mathematics is very similar to this in terms of the instability that you were seeing earlier that took a homogeneous fluid and broke it up into fluctuations that grew rapidly. So it's an instability that's inherent in just because the field is oscillating and there are interactions, it makes this instability grow. You might perhaps worry that all of this I'm talking about is because I did something very special in the initial conditions that you couldn't see. I put some very special initial conditions that gave rise to these localized structures. I want to convince you with this animation that there is nothing special in the initial conditions. This time you saw that it was not a spatially homogeneous initial conditions, it was much more, it's really drawn from some sort of a thermal distribution, it still goes into these localized structures. So this formation of these localized structures in this series is a natural attractor solution. I don't have to do much in terms of the initial conditions to end up here, which is what makes it exciting to me. Indeed, it was a paper in 2008 which sort of described this movie that I just showed you that got me attracted to it because of this general behavior that you get these localized solutions without anything specific. They're natural attractors in the space of solutions. Okay, so this is all nice and fun in 1D, okay? But till at that time, this was, when I first started my first postdoc, this was all done in 1D. And people had not really, and for a long time, people had wondered that, yes, sure, 1D, solitons exist in 1D. This is known for a while. But what happens in cosmology, you should be thinking about one-dimensional systems. You should be thinking about three-dimensional systems. Does this phenomena persist? With the simulation that I showed you, you already know it persists, but at that time, this was new. Okay? So
Sorry.
at that
Mustafa, can I ask a question?
Yes, please.
So with respect to the one-dimensional stuff, are these eventual structures that form, are they really static, or they keep evolving in time?
So their energy density is fixed, okay? The field amplitude evolves, it's oscillating inside them.
Is oscillating in time. Is there any so if the energy density has a fixed sort of random profile, this smells a lot like what we call random singlet physics in 1D condensed matter systems, which is basically, it's not quite Anderson localization, but it's a phenomenon that can happen in spin chains where you get these states that look like wave functions that basically look like random telegraph signals. And I wonder if there's some relationship to these structures that appear in this sort of dynamics.
I see. So Matt, I don't know for the spin chain connection, but I know that these definitely have a very close connection to the types of solitons that Randy simulates in the lab. Right?
I see.
So if you averaged out the oscillation of time, so that you constructed an effective theory that was had averaged out the time oscillations, they essentially will follow an equation that looks close to the Gross-Patievsky equation.
I see.
So they're very, but you have to integrate out the time oscillations to really get an effective equation that looks like that. You can't do it otherwise.
Sure. Okay, thanks.
Mustafa, I have a related question.
Yes, please.
So it seems like a few slides back that you got rid of quantum fluctuations. H bar went to 0 and went to infinity. But doesn't this effect, in fact, depend on some fluctuation to establish some seed of a fluctuation in order to start?
That's right. So when I say that slide was somewhat heuristic, what I meant by that is that in the time evolution, I don't worry about quantum effects. But the initial conditions, I seed them using vacuum fluctuations that should be present in this field. So the initial conditions involve vacuum fluctuations, but then the time evolution of the system, I'm assuming because the state is highly occupied, and this is almost homogeneous state with a high occupation number, I can pursue the time evolution using classical field equations.
Okay.
So you're absolutely right that quantum mechanics, you can't get it because I need the fluctuations to begin with. So those are there. And these are essentially the same fluctuations that on very large scales, those are the same fluctuations that are seeding galaxies and so on. So you can't get away from the seeds of quantum fluctuations that need to be there. But the time evolution, I'm claiming that you can get away by doing a classical time evolution.
Mustafa, what sets the characteristic size scale? It looks like X is about 10 there.
Okay, good. So thanks for asking. I will go back and just, I should have said it here. Too far back. Okay, so this is the potential that determines the dynamics. There's a mass scale. So this is the mass of these particles that appear in the system that make up the field. M inverse, so M is the mass scale. So the Compton wavelength associated with that is 1 over 1 over m inverse and h bar c equals 1 units. Okay, or 1 over m is the Compton scale. So when I use units here, it's in terms of the Compton scale of these particles. So roughly these particles are about 10 to 100, depending on which theory you're in, Compton scales. These solitons, that's how big they are. If you want actual numbers, it depends on what this mass of this particle is. It could be, if you make it very light, meaning the mass very low, it could get to be centimeters, but if you make the mass very heavy, it could be subatomic. So it's really the Compton scale. This is in units of the Compton scale of the particle. Does that answer your question, Pat?
Yeah, thanks.
Okay. So sorry, I'm not including the reason. So everything, all the units, by the way, here I removed the units, but previously there were. So this m inverse is an h bar c equals 1. This is in units of the Compton length of the particle. Okay. So here's the same phenomena now happening in full 3 dimensions. For this system that I'm describing, these solitons exist in 3 dimensions. It's not just a 1-dimensional phenomenon. Okay? Here, instead of showing you the field, I'm showing you the energy density surface, so that this is an overdensity of about tens, or if you wait long enough, about hundreds compared to the background. Okay? So it's a highly dense region of space that remains dense over time. So these are, in that sense, localized solitons that just remain as they are. Again, this is going back to Matt's question and what everybody asked. So that is the density picture. Now, if I take the previous picture was a density picture. If I take a slice through this, if I look at the field is actually oscillating up and down in time. Okay. In this case, this is quite, at least when I first encountered this was quite unusual. Okay? Usually, if you think of this perturbation in some field, you imagine that this is just going to disperse out like a ripple. But here, because of the nonlinearities, this oscillating field holds itself together. So these objects, these types of solitons are called oscillons. They're oscillatory in the field, they're spatially localized and exceptionally long-lived. In terms of simulations, they last for billions of their oscillations. Okay? So in terms of the characteristic timescale, they can last a very long time. Why do they not last forever? Because there's a small amount of this field, the radiation of this field itself, not coupling to photons, just radiation of this field itself, that leaks out of the system that slowly makes this decay away. So it's not perfectly stable, but it's exceptionally long. This question of why these things are long-lived has actually puzzled people for many, many decades now, since the discovery in 1970s. And for a long time, people had been able to figure out why their lifetimes are long when the amplitude of the field is small. But only recently has there been work, and I should give credit to my graduate student, Hongyi Zhang, where we published results of why these objects are so long-lived, even when the amplitude is large. So this was a recent paper that we published this year, and Hongyi was the main author, where we calculated the decay rates and lifetimes of this object and showed with these calculations why what people had just seen numerically for so long, these things live for billions of their own oscillations, why that comes out. Again, this gets a little bit technical, so I'm happy to talk about this in the question answer session if the people are interested what this calculation means. Okay, so we've produced these solitons. They seem rather easy to produce, okay, in the fields that I'm talking about. What I want to now know is what do they do? Okay? So they're produced, do they just sit there? Do they interact with each other? Do they smash into each other? What kind of dynamics will they have? So if you want to think about the long-term dynamics of the system, it is impossible, at least in a cosmological astrophysical setting, to ignore gravity. You can make some things happen on short time scales and ignore gravity, but on long time scales, even though gravity is generally considered quite weak compared to other interactions, over time and over large distances, it will make things cluster. But to truly understand what gravitational interactions are going to do to this system, you have to somehow resolve this fast oscillatory timescale and the long timescale over which clustering will take place. This creates a huge dynamical range problem if you're trying to do simulations. You have to resolve this fast timescale and you have to resolve the timescale over which gravity tries to cluster things together. So what we did in a recent paper, this is with Philip Motz, we integrated out the fast timescale in the problem, which is this oscillation timescale, and derived some effective equations which still describes the long range and long timescale behavior, as long as we are not talking about timescales that are on timescales comparable to the oscillation timescale. So we did that, and we were able to carry out these simulations. Indeed, the picture that I showed you earlier, the first movie that I showed you was already involved that sort of an integration over time. The other movies that I showed you in the middle did not involve that, but this one does. So what happens in this case? Okay. Well, we expect things to cluster gravitationally because now we have included gravitational interactions. These two figures that I show you here, actually, one includes gravitational interactions and one it does not. I certainly don't have the expert eye to distinguish the two just by looking at it. But it turns out, of course, that if you actually do a careful analysis of this, that is, you consider the two-point correlation function of the locations of this, you can immediately pick out that gravity is active. So here is a plot of the two-point correlation function of the positions of these solitons as a function of their separation. The dashed curves indicate when we've ignored gravity, the solid lines indicate when we've included gravity in these field simulations. And you can see that the dashed curves never really arise above zero. Zero is basically a Poissonian distribution of these things. Whereas in the case where gravity is included, you nicely see clustering taking place. This is why the correlation function is positive and grows. This is because of gravity. The colors here indicate that what was there at early times, blue is early times, red is at late times. An interesting bit here of physics is that initially the correlation is negative. That's really arising from the fact that the formation of these objects in these simulations is due to an instability that has a characteristic scale. There's a characteristic wavelength at which there's an exponential growth of the instability, which is dominant, which sets a scale at which these solitons form, how far apart they are formed. So initially, they are somewhat more farther apart than you would naively expect from Poisson. So that's why there is a negative correlation initially. Okay. So, okay. I've shown you that these objects under the influence of gravity can cluster. If they cluster, that means they're going to get close to each other. And now you have to think, what kinds of interactions are they going to undergo? If they smash into each other, or if they come too close to each other. They undergo some rather interesting interactions here. So let me just show them to you. This is on your left-hand side of your screen. You see them undergoing interactions here. It's probably not so clear, so let me zoom in and show you the zoomed in version of this. So one example of this is these objects forming and then they're coming close to each other, focus on the center of this blue circle. Hopefully you notice that they merge together. So two of them came together and merged. The reason they seem to be getting smaller is just because the universe is expanding. So compared to this, the scale of the box, they seem to be getting smaller. They're not really getting smaller here. Okay? But you notice that they can merge together. Another interesting bit is that these objects occasionally can bounce from each other. Again, I'm showing you this bounce. So these objects can interact with each other in ways where they can merge or they can bounce. Moreover, as you will see in this one, they can also form orbits. Okay? So they can be captured in each other's orbits and go around each other. So all of these interesting behavior becomes possible because gravity was able to bring, after formation, was able to bring them together and start off these interesting dynamics. Now, Randy, of course, will be familiar with what is going on in the system. For particle physics, in some sense, initially, it's not so clear because these are just scalar particles. Okay? If you just think from individual particle perspective that makes up this field, it's not so clear why they should have different interactions. Okay? These are objects made up of the same types of particles. Why should they have different interactions? But the reason they can have, these blobs can have different interactions is because they are really, you should think of them as a coherent field. Okay? and fields have phases associated with them. So in this context, if you think of one object that's sitting, let's say by itself, and its field is oscillating inside, it has a time-dependent phase that you can think about. Another object nearby, which is also coherent in its own domain, and it also has a phase. These two, even though the individual phases don't hold much meaning in their absolute value, the relative phases do hold meaning. So when the relative phases of these two blobs are equal to each other, okay, then they will merge. Or they're close to each other, then they will merge. If they're opposite to each other, that is, they're off by pi, they tend to bounce off each other. So it's a relative phase that the fact that these are coherent sort of fields that are oscillating in their own regions, and the fact that they have a phase associated with them and the relative phase has meaning here, that you get these different types of interactions taking place. Okay, so it's important. If you just had an incoherent bag of particles, this wouldn't make much sense. You would have the same type of interactions. But this is a field, and the field can have these more interesting interactions. You would never see these kinds of interactions if you were just thinking of an incoherent collection of particles. And here again, I should give some credit to a couple of undergrads here at Rice. Well, Anamitra is at Rice and Rohit is at Berkeley, who have been doing these simulations recently and exploring more about these interactions, about what's going on in this case.
Mustafa,
yes.
There's a question from the audience. I'll ask it for them. Ray Hajimoto is asking, when the merger occurs, are there any external signatures like gravitational waves that you would expect?
Ray, that's an excellent question. And maybe it seems like I've planted you, but wait 2 slides and I will actually talk about exactly those things. Okay, so we'll talk about the signatures that happen because of these mergers in a couple of slides from now. Okay, so if you can wait for a couple of slides, I'll do that.
Yeah. Mustafa, and a quick question. You mentioned the universe expanding.
Yes.
And if that happens, you know, what happens? So that's sort of mimicking the Hubble's law, right? So if objects are farther apart, they accelerate, or the velocity, you know, is great as distance. But in these pictures, it doesn't seem that as the universe expands, the space-time frame does not seem to drag these particles farther away from each other. Should it?
So so the space, I mean, in some sense, you should think that the particles are, how should I say this? This frame is co-moving, which means that each location in the frame, even if the particles are moving away from each other, you wouldn't be able to see in this frame. So if I was simulating in real time, this whole thing would each box would be expanding in time. Okay, so maybe I can say it better by showing you this movie. Okay, so this movie that you have been seeing. If this wasn't an expanding universe, initially you would see that these objects are moving away from each other. Okay? However, because gravity is active, gravitational force also tries to pull them together again. So then they start clumping together and no longer flow along with the Hubble flow. So it's the same argument for why, you know, when you form a galaxy, different galaxies might be moving apart from each other, but the stuff inside the galaxy, because they're bound together gravitationally, they're not expanding with the universe. So it's not so obvious in this movie, but initially these objects do actually separate from each other. They're in co-moving coordinates, so you can't see that very easily. But at later times, gravitational clustering sort of prevents you from seeing that it holds them together and you can't really make out that there's any expansion in the background. Does that make sense? I didn't explain that very well. Let me see if I can.
No, that was good. No, that was good. Sorry, I was just muted. No, that was a great explanation. Yeah.
But there is, in these small scale things, when you're only talking about interactions of these things, gravity usually is important in bringing them together, but the expansion of phase is almost irrelevant. This is on a very small length scale compared to the scale of the universe that you have. So you only see expansion on large length scales. On short length scales, it's not visible at all. You can almost think of it as, you know, in terms of Hubble's law, V equals H times D. If your D is very small, that is your small length scales compared to the 1 over the Hubble scale, then you won't see much of the expansion effects. Okay. Let me, as Ray asked a question, you know, what about the implications? These things are crashing into each other. So far I've told you they form quite naturally, including gravitational interactions. They seem to crash into each other quite as well. So what are the implications of this that I've told you? Okay. There are two types of implications we can discuss. We can discuss gravitational implications of what's going on, and we can talk about non-gravitational implications. Okay? The gravitational implications, gravity is always active, so there's nothing more to add. For non-gravitational implications, some implications are there just from the field that I've described, but for more observationally friendly things, you might have to couple this to more fields, and I will talk about that as well. But first, let me just say that these observational implications that I can talk about, because I've been talking about general phenomena, let me again separate them out. That if this phenomena that I'm talking about is happening in the very early universe, then the implications could be things like how does the energy from this infraton field get transferred into other fields? If these localized structures form, that will change the way the energy is transferred. That's one implication. The formation of these objects, because they are dense clumps forming out of a homogeneous distribution, that introduces quadrupole moments, which in turn generates gravitational waves. So you could get gravitational wave generation from the very early universe. Also, these objects in some cases can be dense enough that a collection of a few of them together or occasional overdensities can lead to the formation of primordial black holes as well. So those are the kinds of which you can then think about if the numbers work out right, which is a hard thing to do for primordial black holes. They could even constitute all of dark matter at the end of today, or you could just look for the signatures as they evaporate. In terms of the late universe, if this phenomena is taking place in this axion like dark matter, then you could look for this kinds of dynamics that I showed could help you distinguish it from more usual dark matter called WIMPs, which are better treated as just an incoherent collection of particles rather than these fields. And they don't have these solitonic structures there. So it could allow you to distinguish between different forms of dark matter. Even in the late universe, they could be sources of gravitational waves, and even under certain assumptions, they could also leave signatures in light. This is a laundry list of things of what the implications could be. If I was giving this talk many years ago, I would have probably focused on the first part, but recently, since the past couple of years, we have been working on the bottom two things that I mentioned, which is late universe and the implications from collisions of these things in terms of gravitational waves and signatures in light. I'm going to focus on these two parts and not discuss everything. If you want, again, I have slides at the end which can talk about each one of these things in detail. So let me talk about the gravitational, about the implications. Okay? Since I'm talking about the late universe, again, let me give you some scales. Pat, you asked at some point about scales, so let me just give you some sense of what's going on here. You correctly noticed that the length scales that I was quoting was about 10m inverse in terms of the sizes of these objects, okay? But it depends on m, what this number actually translates into centimeters, or what you have. Just a reminder, this m is the mass of the particles that make up this field. Okay? So if this mass is 10 to the minus 2 eV per c squared, then this is of the order a fraction of a centimeter. But if you make this mass very light, 10 to the minus 14 eV, then this could be as big as the solar radius. Okay? So it depends on what this mass is. You might say, how do cosmologists not know what the mass is? And the reality is that what we know about dark matter is more from its density, meaning its gravitational implications care about its density, which is a product of the mass of the particles and the number density of those particles. So you know the product of those two, you don't really know what the mass of the particle really is. So it can be a very broad range. So we don't know it yet, so it can be in either of these regimes, or even broader than that. So the length scale of these objects for the dark matter part could be could be somewhat small, or it could be macroscopic and even astrophysical scales. Usually we'll be thinking about them as macroscopic, but not really astrophysical, apart from some cases that I will describe. Okay?
So Mustafa,
yes.
Do these objects collapse like attractive BECs collapse beyond a critical density?
So I haven't seen them collapse in terms of if you only have their scalar field interactions, I haven't seen them collapse. If you have gravitational interactions, yes, they do collapse. But one place, Randy, where they do collapse is this potential, if you notice, in terms of what you're familiar with, there would be a lambda phi 4, lambda phi 6, and so on. That's what it would, if I only include the lambda phi 4 term, then they do show collapse. If I include the lambda phi 6 term and so on, then I don't see the collapse.
So it seems like that would be an observational signature of either the density or the potential that they interact under.
Absolutely. So I think in some cases they can, absolutely. So if you find that you see these signatures of collapsing things bringing out a lot of radiation in these scalar quanta, that would be an indication of what this potential is. But I think for most cases, it would be, the total potential can't just be lambda phi 4, because then, as you can imagine, it would go negative, and that would create instabilities. Right? So it can't end at minus lambda phi 4. But it could happen that the domain of the potential that the field explores could just be up to lambda phi 4. In that case, collapse is possible.
Mm-hmm. Okay,
Mustafa, I do have a question for this figure.
Yes, please.
This Edison. You have the parabolic potential that goes like phi square.
Yes.
But then you actually have this potential asymptote to some sort of a flat level at large phi. So does it mean that the nonlinear term is actually negative? You go away from phi?
That's right. So the initial correction is absolutely, it's negative. The nonlinear parts are negative. It doesn't have to asymptote to a constant. For all the dynamics I'm talking about, what you really need that it's quadratic here, and it's flatter than quadratic. Yeah, it doesn't have to be perfectly flat. It could be linear for all we care.
But either way, it has to be something that is negative and cancels the phi square, right? I mean,
that's right. So it has to be. So an example, if you were willing to, if you were willing to cut it at some finite field value, even if this whole potential was just a cosine, okay, a cosine would be quadratic at the minimum, right? And then it would have a flattened piece as you go up to the top. So that's an example of a potential that actually appears in this context. Here I'm extending it further out because there's motivation to do that, but you could just take a cosine potential and it would have this shape, at least up to the finite value of the field.
Looks to me more like a hyperbolic tangent square or something like
that.
So
this one, so that's a wonderful eye in some sense, because actually this is a hyperbolic tangent, what I've drawn here.
Okay.
The actual shape is a hyperbolic tangent. But the details of the shape don't really matter too much, okay? A hyperbolic tangent, or I could take a potential that is something that is 1 plus phi squared, the whole thing square rooted, okay? That would also have a shape like this. You have to subtract off a constant, but that would also have a shape that looks similar to that. For the detail shape, for the dynamics, it doesn't really matter, okay? For the details of how long things live and so on, it matters, but this formation of these objects and so on, it's really independent of the detail shape. All you need is a quadratic minimum and something that's flatter than quadratic far away. The flatter and quadratic, as I was saying, this negative, the fact that it's getting flatter is an indication that there is an attractive interaction. One way of seeing this is just think about a bunch of quanta. If you just try to calculate the energy of it, it would just fill up as m squared phi squared. But this negative piece is telling you that the energy is somewhat less than m squared phi squared. So there's a binding energy that's holding, the negative binding energy is holding these things together. That's another way of thinking why this shape of the potential matters. Okay, Edison, did I roughly answer your question?
Yeah.
Okay,
sure.
Okay, so one thing to note is that the scales here, and I'm running out of time, so I'll speed up a bit. The scales here, the length scales I've talked about, and then there's also a mass scale of the object itself. You know, how massive is this object? This is somewhat surprising because even though the scales can be microscopic, you can pack a lot of energy density, of a lot of energy or mass in a small region of space, okay? So you can get huge masses in small regions of space for these fields. All right, let me just quickly go through the implications. First, I'm going to talk about gravitational implications. This is this question that Ray Hajimoto raised about what happens when you crash into each other. This is done in the context where I look at really dense clumps, and I'm going to ignore self-interactions to an extent. They're held together by gravity here, and I'm going to smash them into each other. This is with full numerical GR. This was partly done with my postdoc, who is now left, Marcos Garcia, as well as collaborators at King's College London. So here there are two blobs that you'll see two blobs that are colliding with each other. Okay? That's the energy density of the blobs. On the left-hand side, I'm showing you the gravitational wave signal generated as these blobs are colliding. So this is the amplitude, the time-dependent amplitude of the gravitational waves that are generated as these objects collide and they're trying to settle down. So it's got a very nice feature that there's an initial burst that comes out when they just smash into each other. And then as these objects try to settle down after the collision, you keep on getting repeated bursts from them. Here is another example where I make the objects really compact. I've chosen parameters so they're so compact that when they collide, and again, this is with full numerical GR, as they collide, they get so dense that they actually collapse to a black hole. So you notice that the object disappears, and what's happening is that they've collapsed to a black hole under the collision. The signal that you get in this case looks rather similar from what you get from collision of black holes. Okay, this chirp and ring down that you see, this ring down of the gravitational waveform is very characteristic of what happens when things collapse to black holes or two black holes merge. We compare this. Yes.
Okay, so these times for this signal, what are the time scales?
Good.
Do they depend on the mass?
It depends on the mass again. So the reason again I feel bad about not giving timescales in terms of seconds and so on, because it just depends on the mass. So So if I give you a particular timescale, it will correspond to one particular mass that I've picked.
Okay.
So it can be very short, okay, for some of these cases. But if the mass of these objects are very big, then they can also be. I mean, just this particular plot that I'm showing is no different in some sense from what would happen if corresponding mass black holes were colliding together. So LIGO sees, you can imagine seeing these signals in LIGO for this particular case.
Thank you.
So here I'm showing you the colored things that you see are really from the simulation of these, from collision of these blobs, whereas the black things are from corresponding mass black holes. So you notice that when the objects are somewhat fluffy, that they don't collapse to a black hole, the signals are very different. If they collapse to a black hole in collision, then the signals are quite similar to what you would get. The final thing, which I call degenerate, is just that I made them so compact that they collapse to black holes before they collide. So in that case, as you can see, it's identical to that of black holes. It's just a test case to make sure that our simulations are doing exactly what you expect them to do. What was the most interesting result we found in this stuff is in certain regimes where you collapse to a black hole after collision, the gravitational waves emitted was actually larger than that from corresponding mass black holes. So this is the compactness of the object, written in units of gm/r, c is 1. This is a fraction in gravitational waves emitted in the vertical axis. The dashed line is what you would get from corresponding mass black holes. Here you notice that there is a domain in which the gravitational waves that are emitted can actually exceed that of what you get from black holes. This is partly because as these objects are coming close to each other, they are more deformable, so they have a higher quadrupole moment, as a result of which you can generate a larger amount of gravitational waves from them in this region. So there's a competing effect of you want to make them compact, but you also want to leave them deformable. And these objects seem to win out in that regard in this regime that I'm showing you here. So this was a fun result to obtain. There are some caveats, how likely are such ultra-compact things to collide with each other. This is head-on collisions. You should really be thinking about in-spirals. In-spirals are hard to simulate because it just takes computationally so much longer to get them close to each other to do this, but we are working on that. And again, distinguishably from a black hole collision, we've seen that at least initial work shows that there is a difference between if you can measure the signal before they merge, that is, as they're going into each other, and if you measure the decay of the signal after they form the black hole, then you might be able to distinguish the two in that case quite well. Okay, the final part of my talk, which is the next few minutes, this is brand new work which we did over the last, we just put out a paper, it's not even published yet, it's just been submitted. This is with my postdoc, Zhonggang Mo, incoming postdoc. Here what we thought about is what is the effect of these dynamics in light, okay? Like if you couple this to light, what happens in that case? These dark matter particles that I'm talking about, axions, have a natural coupling to light, which is written like this field phi, coupled to FF dual. You want to think of this as the field coupled to E dot B, where E and B here are your electromagnetic fields. Okay, so that's the coupling of these fields. The essential idea is that if you take two of these lumps and smash them into each other, before they smash into each other, they don't emit any light. Okay? They behave like as if you can't see them. They just behave like regular dark matter. But if they smash into each other, there is a threshold that can be crossed where these objects can literally, that very quickly burst into a flash of light. Okay? So let me, instead of talking so much, let me just show you a movie. Here are these two objects going close to each other, smashing into each other. Notice nothing happened before, but as these objects settle in, on the left-hand side, you are seeing this huge flash of light being emitted. What's happening is really a large fraction of the mass of these solitons, as they're settling in, is getting converted into electromagnetic radiation. This gives you hope that we might even see the smashing of these objects in the sky. Even if they're rare, we might be able to see them. Okay, there's just more details. Important things that before merger, there's no emission. As they merger, there's a resonance and threshold effect that really makes them go off into a lot of electromagnetic radiation.
Mustafa, how does a dark matter, how does an axion couple to electromagnetism?
Right. So so let me go back and say this. Okay. So in general, it's true that you think of dark matter not coupling to electromagnetic waves or anything else, right? That's what we mean by dark matter. But the reality is that dark matter at some level, the fact that it was produced in the early universe means at some level it must interact with the rest of the world. At some level it has to. In these types of dark matter, this is a natural coupling that comes about. This coupling is very, very tiny. Okay? It's very difficult for, in usual situations, if you just took dark matter particles and asked, if two dark matter particles come together, will it go into photons so easily? The perturbative decay rate is exceptionally small, which means unless you are in these special situations where these dense clumps collide, these particles would not decay into photons. They would not go away, so they would remain stable. It's in these special situations where these high density clumps with a coherent field inside them, when they come together, you get these flashes. So it's a really cool phenomena where these are fine as dark matter, but in these special situations, you can get these flashes of light, which can give you insight into what the nature of dark matter is. This coupling, by the way, is also what is used, Randy, for many strategies for detecting axions in the lab. But it's very hard because this coupling is very weak.
But I guess here in the scenario that you're envisioning, you have competition between electromagnetism and gravitational waves.
Yes, but electromagnetism will win out, big time. Okay. Even though this coupling is small, the electromagnetic phenomena, this is a resonant phenomena, whereas the gravitational one is just sort of a force. It's just gravitational radiation is coming about because these things are deformed. In the electromagnetic phenomena, you're literally converting the rest mass of these particles into radiation. So it's a much more energetic, much more efficient phenomena in that sense.
Mustafa?
Yes.
Are these oscillons or whatever the dark matter particles you call, are they their own antimatter, or they actually have an antimatter counterpart?
They're their own antimatter. Okay? So the particles that make them up are their own antimatter. It's a scalar field without any. It's a scalar field without any charge. So they're their own antiparticles. So they can annihilate to give you photons, for example. Okay? But the probability of that happening, if you're talking about individual things, is very low. It's only in these situations where what's really going on is there's a huge amount of Bose enhancement that happens. Because these are high density regions, you're overlapping them in some finite region of space, you suddenly produce a few photons, and this process exponentially grows very rapidly. So a condition has to be satisfied when they merge, that's a threshold effect, and then Bose enhancement takes over and really produces photons rapidly out of this. So I think it's really exciting, it's really cool that something like this happens. And we actually did simulations with full gauge fields and all of these things together and really saw this happen recently. Again, this is in simulation, we haven't seen it in the sky. Okay, so let me just say that 30% of the total energy that you started with, the rest mass energy you started with, goes into scalar radiation, meaning just radiation of the axion field itself, and 20% goes into electromagnetic radiation. But this is a huge amount because you're taking the rest mass of these things and converting into radiation. So it's a massive thing that's going on in the sky. Just to give you numbers, oh my God, I'm so late. Okay, you have radiation here. To give you some sense for typical numbers, this could be 10 to the 36 GeV going off into radiation in the sky. This is, again, for astrophysicists, this is still not such a big number because supernovae are much bigger than this, but still, it's an astrophysically not a negligible number, amount of energy in radiation. And then the frequency again, and this depends on the parameters, but I'm going to go through this quickly. There are some caveats. Related to this, please ask me about what is really missing in here. There are things about rates, things about how long these things survive and so on are important. I'm going to skip through this. Future directions, of course, looking for multi-messenger signals. Fast radio bursts, these are phenomena that are as yet unexplained. Could this, what I'm talking about, have some contribution to the fast radio bursts that we are seeing? That's something we are thinking about. Again, with Chris, for example, something Chris Tummel works on, there was a recent discovery of access in xenon 1 ton, where part of the implication could be that very highly energetic dark matter particles are creating that access signal. There are other explanations as well, but highly energetic dark matter particles produced from these collisions. Been thinking about this, but again, I don't know if it can explain it. Finally, I talked about electromagnetic production. You could also talk about fermion production, which comes from a similar effect. And with the student Ray, as well as with Andrew Long, we are thinking about this at the moment as well. So lots of things to do in this direction. I think I'm going to skip the tangential digression. Sorry, Randy, I was going to talk a little bit about a connection to BECs, but you can ask me later about how this all connects together with BECs in the lab. Another tangential digression was related to Matt's work, which I did with Matt's postdoc about Anderson localization and cosmology. But again, I'm going to skip through that and just provide you with the summary. So the summary is that in very general situations, scalar fields with potentials that open up away from the minimum can give rise to the formation of these solitonic structures. Under the influence of gravity, they undergo some interesting interactions, including bounces, mergers, and so on. And in certain situations, especially in the late universe, you can take these objects and produce significant amounts of gravitational waves, or even huge bursts of light that we can hope to observe in the sky. I like it because the dynamics are general, and this is something it doesn't seem to rely too much on the details of initial conditions or the details of the system. However, they seem to be relevant to two interesting areas in cosmology that I'm interested in. And what also interests me right now is that given the observational implications, if we see these implications, it actually could give us insight into dark matter, which is hard to get otherwise. Small couplings still giving you big effects, at least in the electromagnetic part. This I think is interesting. And I hope we can make some progress in this in the coming years. Okay, thank you everyone.
Thanks for the wonderful talk. So there is time for questions. I'll start with the one which is in the chat. Taylor Carnahan would like to ask a question. Taylor, do you want to go ahead and ask your question?
Sure, yes, sir. So, Dr. Amin, would you be able to distinguish between a dark photon and a photon in the scenario of the EM pulse?
Yes, so I mean, here I'm literally talking about photons, right? So you would be able to see it with regular detectors. If it's a dark photon, I can't look at it with a telescope. You would have to look at it with a detector, which takes the dark photon and converts it into a signal that we can see. So it interacts with regular matter in some way that we can then detect. So certainly these signals that I'm talking about are about real photons. Could this phenomena also happen in dark photons? Yes, but given that this can happen in real photons, I'm much more excited about that first, because this can actually be seen in the sky.
Sure, thank you.
Matthew Baring has a question.
Yes, Matthew.
Yes, Mustafa, since you showed the gravitational wave signals and it was a 1D simulation and much of what you talked about is 1D, how can you port in spin, angular momentum, rotation into your system? And what do you think would be the key signatures with some of these observables?
So, Matthew, the simulations are not 1D, right? So the simulations are full 3-dimensional in almost everything I showed. It's just that this collision that I'm talking about, I did it along an axis.
Right.
So the full simulations are done in full 3D. So there is a symmetry here, absolutely,
Okay.
In terms of the dynamics that I'm using as initial conditions. But the simulation is full 3D. So your question is, what happens in the case with spin and angular momentum and also in spirals? So I think, let me answer first in the context of these photon production. In the photon production case, it really doesn't matter how I got there, okay? As long as I have two systems that come together to form a larger lump compared to what they started with, okay? So there's a characteristic scale that they start with. As long as they form a larger lump that is relatively settled, there's a resonance condition that gets satisfied, and then it produces this. Mm-hmm. If you have really high spin for these objects, then you wouldn't get these. What you would find is that it wouldn't be in its ground state. It would radiate away the spin because here it can do so with a scalar radiation and settle into its ground state at some point. And then the same phenomena would take place. So I don't think it is that sensitive. If you started with spin for these objects, they would radiate that away and then settle into the lowest energy state they could, and then this phenomena would still take place. In the case of the gravitational wave production, I don't know the answer there because we haven't done it. But what I would expect is that when you have in spirals, the fraction of energy in gravitational waves should actually go higher because that's what you see in black holes as well. In terms of actually what the details of the signal, how the waveform would change in this case, that I don't know yet because we haven't really thought through what spin would do to the system in that context.
Yeah, I mean, one of the reasons I ask is because of the black hole mergers, there's a long chirp.
That's
and so
right.
There's a lot of oscillation, a lot of structure in that, and that gives them an angle, a handle, diagnostic handle on the mass ratios and the momentum. And so therefore I wondered if you could do the same type thing with this.
Yeah, so I think that's exact. So we are actually doing this, Matthew. So for example, here, when you do the in-spirals, we actually get the usual phase information from the early times when they're not close to each other. That information, as you said, will give us indication of mass ratio. And then the hope is that after the collision, we'll look at the ring down and compare the mass ratios from the beginning that you would get from, because for black holes, the initial phase would tell you what is happening, what should happen at the end, modulo spin for the moment. Mm-hmm. We're trying to do the same thing here. Once we are able to do that within spirals, but not giving the initial object spin, then we will move on to thinking about giving angular momentum to the initial objects and then trying to see how that changes the signal as well. But it's just that, Matthew, as you know, the problem with in spirals is that things take, numerically, they take a long time for things to come in together. And if you don't start them far off, then you're not starting them with the correct initial conditions because then they're interacting with each other when you start them off.
Yeah,
they're not the correct physical situation that you would get into. So it's a bit tough for us to do right now, but we are working on it to see how we can improve on that.
Mm-hmm. Okay, thank you.
Mustafa, Edison has a question.
Yes. Mustafa, can you kindly go back to the cartoon that you had in the very beginning of Scott Russell?
Okay, yes.
It's related to my question. Yes. So the solitary wave that I am more familiar with and I teach in my course are ones that actually do not oscillate, and they actually propagate with a constant phase and group velocity, and therefore you see that the water lump just keeps going downstream without any change. In your case, your oscillons are actually oscillating in place.
Yes.
And are you telling us that is it true that the oscillons actually have zero phase and group velocities?
So no, so they
in both 1 and 3D.
So no, they actually move, right? So but they move, this oscillation, they move together. So it remains coherent, okay? And this oscillating field just moves as a whole. So imagine this water wave, but as it's also moving, it's also oscillating. Now, an important thing is at slow speeds, that's what it will look like, okay? It just looks like this wave this water wave that's just also oscillating as it's moving this way. But as you go to relatively slightly faster speeds.
You mean in your case? In your case, it's oscillating, not in the case of water.
Not in the case of water. In my case, it actually oscillates as it's moving. Okay. And it maintains that coherence as it goes on. But if you actually look at what the profile would look like if you move at somewhat semi-relativistic speeds, then you will actually see structure here, because as you know, the space oscillation in time will leak into spatial oscillations and vice versa. So it will actually look like a localized wave packet that's traveling. So it will look like a wave packet that's traveling, but the wave packet maintains its shape and it does not disperse. So it remains a soliton, even though the amplitude of the field is changing in time and even has some structure in space, but it maintains that structure and as it moves around. So that you can literally think of these as wave packets that stay together, don't disperse, they move around.
Okay.
But yeah, it's a different kind. I mean, this is why people for the longest time didn't think that these things existed or believed that they were real. Because this intuition that, oh, these are nothing like what we know. Indeed, it actually in 3D, the reason people thought they didn't exist is because it violates a theorem called Derrick's theorem, which is an energetics argument to say that in 3D, you can't have static stationary solitons, meaning, but the reason these solitons exist in 3D, but in this context is also because they have a time dependence inside them. So a condition of Derrick's theorem doesn't apply, so they can't exist in 3D. And this is why people didn't believe they existed for long.
Thank you.
Well, I'm afraid given the lateness of the hour, I propose that the rest of the questions we relegate to an unofficial part. Unfortunately, as in these times, we can't have the wine and cheese. So Mustafa, we can't ask you questions over a drink, but maybe we can still ask you if you could hang around after the talk.
Yes, absolutely. And again, let me apologize. I went over, I realized after the fact I went over by 10 minutes. I'm really sorry that I did.
No, there was a lot of questions during the talk as well. On behalf of everyone, let us thank Mustafa again for the wonderful talk and stay on if you would like to ask questions.